Hello there, this is Mrs. Lemke. I'm here today to talk to you about something that is twice as fun, and that is the double angle formulas. So at the top of the notes or on my screen, you can make your own chart if you're drawing on your own paper. I'd like you to try to fill out this chart, and there are some famous angles here, asking you in the first column here to tell us some things that you should know off the top of your head, and then in the middle column asking you to double each of those answers, see what you get. And then over here, because of the parentheses, understand that you do the doubling of the angle and then apply the trig function to that, okay? So please pause the video, fill out the chart, come back and we'll chat. All right. So you should have the values that I have here. And then there's this hefty word observation underneath it. And the observation, I thought for a second that maybe what Mr. Covey meant when he made these notes was that I should see a pattern or something. But then I thought about it and I realized all he wants me to notice is that these are not the same. Right? Because a person might accidentally think that 2 times the sine of an angle and the sine of 2 times the angle, you might accidentally want to put a equal sign here, when in actuality, should be a not equal to. Right? That's not a thing. Like, just look at the cases we have. If you have a counterexample, that's enough to disprove something. One example can't prove it, but one counterexample can disprove. And if you look here, 2 times cosine of an angle versus cosine of 2 times that angle, those are not the same. Okay, so that's good to know. Now that really isn't super duper surprising if you broaden your mathematical thinking to other things that you may have seen where you have a function and you compare 2 times the function versus the function with double something plugged in. So like what I mean here is let's remember what square root of 9 is first of all, that's 3. And then the comparison we're making is over here. So is it the same to say 2 times root 9 as it is to say 2 times 9 and then square root? Well, let's work them both out. So 2 times square root of 9 would be 2 times 3, which is 6. Whereas over here, I have square root of 18, which I'd actually break down again to have it as root 2 and root 9. So I'm kind of going in circles, but just talking. And then square root of 9, as we said over here, was 3. So this is 3 times root 2. And 3 times root 2 and 6 are not the same number. They're not decimal equivalents. It's not like they're the same number, but just different forms. They're not the same thing. All right, you may also remember, oh, it'd be so great if you do remember this, logarithms. Oh my gosh, logarithms. So the base 10 log of 10 is asking you what exponent goes on a 10 to make 10. Like this, 10 to the blank equals 10. I'll write it up here bigger. Okay, so what number is that? 1. Okay, so and the default base on a log is 10 if nothing is written there, like a little subscript. Okay, so now that we remember that the base 10 log of 10 is 1, I know that this is 2 times 1, that's 2, whereas this is the base 10 log of 20. In other words, 10 to the blank equals 20. I think I need a calculator for that. So I pulled out my calculator and I got 1.301. 2 and 1.301, not the same number. So you see, it's not super surprising that you can't just pull this 2 any which way you want, right? You could think of other examples maybe. Can you think of any other examples? Pause for a second, see if you can think of another example. Okay, well, the example I thought of was cube root, and I thought of cube root of 8 and how it equals 2. And so then I thought about if I had a 2 on the outside versus a 2 on the inside, would I get the same thing? No. One way I get 4, the other way I get cube root of 16. Cube root of 16 isn't 4. Square root of 16 is 4, but not cube root of 16. So in general, as long as you just said something where 2 times a function is not the same as putting 2x into the function. That's the deal, okay? Whatever examples you thought of. All right, so how do you find the sine or the cosine of a double angle? That is the question. Well, I'm telling you guys, it just comes down to knowing two more identities. These are great identities. They are wonderful. I'm going to put a star by each one. Ooh, actually, maybe I should put smiley face by each one. So they do make us happy. Okay, so sine of 2 times an angle. We're using a here to kind of help you think of angle. So sine of 2 times an angle is 2 times the sine of the regular angle. Now notice this argument here is a. The argument here was 2 times a, right? So this number, like if it were 60 degrees, this would be 30 degrees. If this were 20 degrees, this would be 10 degrees, okay? So make sure you're paying attention to that. So the sine of 2 times something is 2 sine of the plane angle, cosine of the plane angle, not doubled. Okay, now the cosine double angle formula is really fun because you can write it 3 different ways, and it all is because of our dude Pythagoras, this Pythagorean theorem over here, okay? So this is the one that I have committed to memory. But there are times when you want to like just tweak that a bit. So over here, Mr. Covey wrote to us, we want to substitute for sine. So take this sine squared, look at your Pythagorean identity. You know that sine squared is the same as 1 minus cosine squared. So I could write this as cosine squared, that's this term. And then in place of the sine squared, I could do 1 minus cosine squared of A. And then if I did a little combination of like terms, I didn't think ahead there. I would have 2, because you see how this minus is going to go minus there and then make that addition. I'd have 2 cosine squared of A minus 1. Boom. Okay? Alternatively, I could go back to this one that I have memorized in my head, and instead of substituting for the sine squared term, I could substitute for the cosine squared. So look over at my Pythagorean bubble over here, my little cloud. Cosine squared is the same as 1 minus sine squared. So where I have cosine squared, I could write 1 minus sine squared, and then I'd still have this minus sine squared. Okay, so my replacement was there on that first chunk. I took this and put it in place of that. Okay, now let's do a little combination of like terms, and I get 1 minus 2 sine squared of A. Okay, so in summary, we would say, I don't know if drawing more on this is going to make it better or worse. Probably worse, but I'm still going to do it. Do you ever just do things like that, rebellious like? Okay, so we are going to put rainbow by the fact that here we have a cosine double angle, and here, and here. I'm for sure bothering Mrs. Fry's aesthetics right now. Sorry, Fry. Okay, we'll get a clean page. It'll look nicer, I promise. I'll never have the good handwriting like her, though, man. Okay, so this first example is very, very algebraic, okay? So they already told us what sine of theta is. They already told us what cosine of theta is. This is legit. Just write down a formula and use it. So the sine double angle formula doesn't have choices. It just has one version. And then you plug and chug. 2 sine was 0.643. Cosine is 0.766. Get your calculator. Type, type, type. 0.985076. Boom. All right. Cosine has choices. I'm going to choose on this problem to use the one I have memorized. In the other problems that are in this video, I'm going to make a different choice just so you can see each of them in action, so to speak. Okay, so there's one of the cosine double angle options. Cosine is 0.766. I'm going to square that. Sine is 0.643. I'm going to square that. Type, type, type on my calculator will give me my answer. So you see, that's literally just plug and chug, my friend. That's straightforward as it can be. Now, in the next two questions, we do get to draw a picture as well as do some trigonometry, okay? So this one said, given that cosine is negative 2/3, and then this bit over here is fancy pants way of saying we are in quadrant 2, because we're between pi over 2 and pi, and that's quadrant 2. So I'm supposed to draw a triangle to figure this out, so I think I'll do that. So I have an adjacent side, or an x, that's 2, and a hypotenuse of 3, and those are negative because if I think of this as an ordered pair, it would be negative 2 from going to the left, and I have to figure out what number goes there. So let's do a little Pythagorean on the side here. X squared plus y squared equals r squared, and y would be square root of 5, and I know that that's positive because of going up in my picture. The y would have to be positive. So there's my picture, and my angle of rotation is theta. Okay, now what I want to know is not the sine of that angle or the cosine of that angle. I want to know what happens if I were to rotate this and then that much again. Okay, so my blue picture here, going right over the 2, is roughly 2 times or double the angle. And so I want to know the cosine and the sine for that rotation. And I don't even know anything about the triangle that I would get there, right? I'd have like some side and some reference angle, and I don't know any of these sides. Okay, that's the magic of the double angle formula. So sine of 2 times an angle is 2 sine of the angle cosine of the angle. And I'm going to substitute in my sine value here would be root 5. Sorry, I got tongue-tied. Root 5 over 3. And my cosine was given in the problem. And so I could just multiply here. Remember, this is like 2 over 1. Just go straight across, straight across. That's how you multiply fractions. And we would get negative 4 root 5 over 9. Yay! Then, cosine double angle. I told you I would use all the different versions. So the version I'm going to choose on this is the 2 cosine squared theta minus 1. And the reason I would choose this version on this problem is, what if I screwed this up over here? What if I have the wrong number? Then my sine value is wrong. However, given in the problem was cosine. So I know cosine is for sure, negative 2 over 3 because it's in the problem. I didn't make that up. The problem made that up. So I'm going to use the version, right, of all these things with the terrible arrows by them. I'm going to use the one that is the least risky, right? Minimize risk. And say, all right, we've got 2 cosine is negative 2 over 3. We're going to square that guy. We're going to subtract 1. Okay, now you should be able to do all this math without a calculator, my friends. Of course, you could use a calculator, I guess, but I would be so proud of you if you knew how to do things like the arithmetic here. 8 over 9 minus 1, or 9 over 9, gives you negative 1 over 9. That would make me proud, okay? Now, an interesting thing you could observe is we got an answer for sine that is negative, and we got an answer for cosine that's negative. And the quadrant in which sine and cosine are both negative is this quadrant here, quadrant 3. So it makes sense, right? You can do a little plus minus check of reality, okay? That is the joy of the double angle formula. Did you notice my pictures? These are all pictures that had to do with double something. Just saying. Oh, look at these cuties. No kind of double like twins. Woo! Okay, so the last example, isn't it? Yeah, it is the last example. Good job, us. Okay, so pi over 2 to 3 pi over 2 is telling me that I'm on this half of the unit circle, or the coordinate plane. I guess I don't have to be on the unit circle, but I'm on the right side because that's what those two angles mean. But then it says sine is positive. So that must mean I am up. Right? I am up here in quadrant 2. Well, that's a really bad picture. Hold on. Okay, sometimes I just think no matter how long I pause, I'm not going to be able to draw well. So this is what we're going with. Okay, if you do Pythagorean theorem here, This missing side ends up being 40, and you're going 40 to the left, so that means our ordered pair is negative 40, comma 9. So that's my x, that's my y, this is my r, okay? And then do your sine double angle. It's such an elegant formula, don't you think? And so sine was given in the question, 9 over 41. Cosine, we could figure out from our triangle and see that that's negative 40 over 41. And then multiply all the things, go straight across the top, straight across the bottom. I'm going to leave it as a fraction. I mean, what the hey, right? You could get a decimal if you wanted. That's an 8, believe it or not. Okay, now the last version of the cosine double angle identity, the one I haven't used yet, is 1 minus sine squared, sine of theta squared, okay? And again, the reason I would pick this one for this problem is that sine was given. So I know that that is a correct value, that I didn't mess something up. So I could just utilize it and do my arithmetic. Oh, wait, I forgot a 2. Oh, heavens, I'm not going back to redo this video at this point, my friends. Sorry about that. Oh, my goodness, I was thinking about Pythagorean or something. Oh, my goodness. 1 minus 2 sine of theta squared. Sorry. Were you having a heart attack about that? If so, good job. You care about the math. That's wonderful. So 1 minus, and then 2 over 1, and then 9 times 9 is 81. And 41 times 41 is 1681. And we would end up with, when all is said and done, with this number or its decimal equivalent. They're happy about it. I hope you're happy about it. I hope you had double as much fun as you usually do in PCA. See you guys later.